So for E2, besides this beta elimination, the alpha carbon is the one where your leaving group is attached. And here your leaving group can be the halogen or your sulfonates, any of those. So on the alpha carbon, you have the leaving group and the carbon next to it. Remember, you have to look at both sides. You also need to make sure that you want to make a ZSAVs product. What is a ZSAVs product? The more substituted alkene. That is what a ZSAVs product is. Regiochemically, ZSAVs is more stable. Stereochemically, the trans alkene is more stable. This is what your ideal aim for the resulting alkene should be. However, depending on other conditions, you may or may not get a ZSAV or even a trans. So when will that happen? Looking at the bases that I have listed here, all of these three bases, the hydroxide, the methoxide, the ethoxide, all of them favor the ZSAVs regiochemistry. But a bulky base like this turboperoxide will favor a Hoffman product or the kinetic product for that matter of fact. So let's look at the examples differentiating these two. And I'm going to draw a square kind of a structure for our example. Okay. Now, where is my leaving group? All of these are my hydrogens. Usually I will not draw out all of my hydrogens. Usually I will just make sure that I have bond line, and I would assume that you understand how the hydrogens or how many hydrogens are there on that carbon. I'm given this substrate and I have this reagent. Remember, having an ethoxide or a methoxide or any alkoxide should be your clue that you're going to see an acid base, a substitution kind of reaction. This is a more basic material than it is a nucleophile. If with this, the corresponding alcohol is provided, then you have to be sure that now you will have an elimination mechanism going on. So this is the ethoxide and this is the ethanol. During the reaction, when the base is consumed, the sodium and this acidic hydrogen replace each other, and then it will regenerate your base. So this part, this oxygen is your base right here. So what are the two requirements that we need for elimination? We need a strong base. We have the strong base. What is the substrate that you need? Tertiary, secondary, or even primary. Do you have a secondary, primary, or a tertiary substrate? Yes.
Secondary.
Yes. Thank you. And this is your secondary substrate. Besides a strong base, what is required of this structure? You need an anti-beta hydrogen. So first of all, where are your beta hydrogens? This carbon, which is directly attached to your leaving group, is your alpha carbon, and the carbons next to it are the beta carbons. Just to differentiate, because this carbon has a methyl, this carbon has only hydrogens, I am going to put a prime here, just to differentiate between the two beta sites. And so I need to take out a hydrogen, 1, 2, 3, or 1, 2. Out of these 5 hydrogens, I will take out only 1 hydrogen. Now look at this. If I take a hydrogen out from here, what is the kind of product that I will form? I will have these 4 carbons, 1, 2, 3, 4 carbons. And the first 2 carbons will get the double bond if I take out this hydrogen. So what is the regiochemistry here? This is a Hoffman regiochemistry. Do you think this will be the major product? It cannot be the major product. Why? Because a Hoffman is a less stable molecule. If the para hydrogen is available on a carbon so that a more substituted double bond can occur, that is the hydrogen the base is going to abstract. So none of the hydrogens from these 3 sites will be abstracted out. Out of these 2 hydrogens only, my base will be abstracting out the hydrogen. So remember, this is not a bulky base. This is a simple sized, regular sized base. So following E2 mechanism, the base will abstract out a hydrogen. Which hydrogen? The hydrogen which is on the same side, syn, or a hydrogen which is on the opposite side, or anti. And so remember, for all your E2 mechanisms, it is the anti or the anti-beta hydrogen that will be abstracted out. So you are going to have this base, it abstracts out this hydrogen, the hydrogen carbon bond breaks, and the leaving group leaves. So this is the exact mechanism that we had looked at for the E2 elimination. Base abstracts a hydrogen, the hydrogen carbon bond breaks, the leaving group leaves. Exactly same. And so I'm going to draw my 4 carbons again. Where are my double bonds going to be? On the second and the third, or the second and the third carbon. And of course, there are hydrogens all over on it. What kind of a product did I make? I made a ZSABS product. So regiochemically, it is a ZSABS product. Stereochemically, what did I make? On this carbon, the bulky group is right here. On this carbon, the bulky group is right here. What is the position of these groups relative to each other? Are they trans or are they cis?
Trans.
They are trans. Very good. So having a ZSAF product with trans stereochemistry is going to be the more stable and hence your major product. This Hoffman will be the minor or less stable product. And hence, when you're given a question like this, you will only be expected to draw this particular product, not the other one. But there is a time when this product will be the major product. I'm going to draw the same structure, same substrate that is. And instead of using the regular base, I'm now going to use a bulky base. Potassium terburoxide. What is terburoxide? This is what a terburoxide looks like. Your metal ion can be potassium, which most probably will be potassium, but sodium can also be right here. So what you have on your hand, butanol. I have a tertiary butanol and tertiary butoxide. Remember, this protic acid, this protic material is only here to keep a continuous supply of your base. So when we will have a bulky base, as it approaches the inner words or inner sides of these hydrogens, remember both of these are beta prime and beta carbon, all the hydrogens on these beta carbons are beta hydrogens. So the bulky base, when it approaches these hydrogens, it will not be able to dig deep into the molecule, but superficially, wherever there is less bulk. So the bulky base approaches the less bulky part of substrate. So will it go in deep or will it look outside? It will just look outside. So this is a special sequence. Whenever you will have a bulky base, you will abstract the proton from the less bulky part. And now still the E2 is following. Still this is E2 elimination. E2 elimination, E2 elimination. And so even though this is a Hoffman product, H, CH2. Hoffman product, less stable, but for a bulky base, this is going to be your major product. Other bulky bases that you can see are DBN and DBU. Those are your bulky bases with which we are going to get a Hoffman product. So let's look at another example. So I have these two carbons, and these are my planar bonds. And I'm drawing an eclipsed conformation. So bromine, any leaving group could have been there. I'm just using bromine because it's easy. Let's say I have a structure like this, and I have my sodium methoxide. I have to identify that this is a base, a strong base. Do I have a alpha carbon here? This is my alpha carbon to which my bromine is attached. If this is my alpha carbon, where are my beta carbons? These two are my beta carbons. Both the hydrogens on this carbon and on this carbon are going to be my beta hydrogens. If I abstract this hydrogen, I will get a double bond here, which will be less substituted or Hoffman. But if I get a beta hydrogen from here, I will get the more substituted ZSABS product. But what are the conditions for E2? For E2, I need a strong base. Remember, I need a strong base. And I need a hydrogen which is anti to my leaving group. Looking at the structure, both the hydrogens and the bromine, are they anti or are they syn?
Syn.
Very good. In this position or in this sequence, the hydrogen is in the same direction as bromine. Before you think about anything else, think about conformation. What did I do? I can rotate my single bond, and this is what would normally occur also. When I will do this conformation, I will keep this carbon intact. So you see how our module 5 is helping us. So all of my groups, all of my groups are there. My hydrogen is there, my methyl is there, my bromine is there. I'm keeping this part intact and I'm just rotating these guys right here. So this hydrogen and this bromine, they were in the same direction. But I want my hydrogen to be anti to my bromine. What has happened to the other two groups? They will also move. So when they will move, when I have rotated it in such a way that this hydrogen goes up, the methyl will take its place. The C2H will take methyl's place. And my hydrogen will take the place of C2H5. Now, because of this conformation, I can rotate my structure. Now my hydrogen is in the anti-location. Now when the base will attack, this bond will break, the leaving group leaves. Now be careful. This is going to be a flat molecule. Okay? My C2H5 and this H, they will be in the same direction. Why? My bromine has kicked out and this CH3. So let's imagine that my Br and my H is gone. So this is gone. These are gone. Whatever was here and whatever is here, I'm going to flatten it. So these two, whichever groups they were, they are going to be at the same direction. So I'm flattening out this, I'm flattening out this, just by removal of this group and this group. The other groups flatten out to make your double bond. So you cannot control the stereochemistry just like that. So my C2H5 and my H, my CH3, at the CH3 and this CH3. Definitely a zigzags by regiochemistry. What about stereochemistry? Is it a cis or is it a trans? First of all, can you use a cis trans or will you use the EZ kind of a notation? We will have to use the EZ kind of a notation. Why? If you look on this carbon, who is the priority group? If you look on this carbon, who is the priority group? And the priority groups are opposite to each other or transkind to each other. So the stereochemistry is trans or E and gen. Do you see how I got this? Not the Z version, I got the E version. Let's look at one more example before we proceed. Let's say you have a cyclic material now, and I have a system like this. I have a similar base. So what is this ET? Is it the Ethereum? It's just another shorthand for ethyl. Okay, so sodium ethoxide. Instead of writing the CH2CH3, I'm just writing ET. Because sometimes instead of writing CH3, I can just write ME also. Just wanted to let you know when you see the drill tests or the exams. So what do I have here? I have a strong base. So there is a probability that E2 will occur. What is the second thing that E2 needs? It needs a anti-beta hydrogen. So for a E2 to occur, and this was also E2 by the way. For a E2 to occur, I need a anti to this leaving group. This is my alpha carbon, this is my beta carbon, and this is also my beta carbon. If I make a double bond here, I will get a Hoffman. But if I make a double bond here, I will get the ZSAVs, the more substituted alkene. But looking at this situation, does this beta carbon have a hydrogen in the anti position? So if this is coming out and this is going at the back, the O-mesylate and the ethyl group, they are trans to each other. They are not in the same plane. So where is the hydrogen of this? The hydrogen of this beta carbon is syn to your leaving group. Is this something that you can fix by rotating on this bond? We cannot do that. So because the anti-beta hydrogen is not available, if you try to rotate it, you are going to just break the bond. You will use the beta hydrogen of other location. Any questions on what I just did? So I cannot use this hydrogen because this is not an anti-hydrogen, anti-beta hydrogen. We are going to use this hydrogen, which is anti to our leaving group. Remember, we need a smooth movement. And so even though this is not the ideal ZSATs, this is the Hoffman. So there are these two reasons that you can get a Hoffman. If you have a bulky base, if you do not have a anti-beta hydrogen. When you get a double bond, no stereochemistry will be present here. Okay, no wedge or dash. The wedge or dash is only present in case of a sp3 carbon atoms. Any questions so far? Okay, very good. So this was our E2 mechanism. The other mechanism that we will usually not see is the E1 mechanism. Okay, so we have looked at all of these parts. E1 mechanism needs very weak base, plus it needs heat. So when I say a weak base, and this should not be H2SO4, it should be water here. You can have water, you can have sulfuric acid, you can have phosphoric acid, you can have any other alcohols or neutral lone pair donor molecules. So whenever we have the E1 likes weak base. So whenever you are doing eliminations and you do not have a strong base, you have a weak base plus heat, then you will have E1. If you just have a weak base or a weak electron donor, then you will have SN1. So the competition between SN1 and E1 is solved by the heat. Usually with heat, we see eliminations. It dehydrates. So just like SN1, what was the speciality of SN1? SN1, leaving group, leaves on its own. Yeah, let's say I have this water and I have heat. So because I have heat, because I have a lone pair, I know it's a weak electron donor, I know we are going to have E1. So these are your clues. Heat, weak base or weak electron donor, and a substrate. Substrate of primary, secondary, tertiary kind. Primary substrates will usually not do E1. So E1 also likes tertiary, secondary, sometimes primary also. So what should be the first step? The leaving group leaves on its own. Loss of leaving group. Whenever a leaving group leaves, that is the rate determining step for all your mechanisms. For every mechanism that you will see, the loss of leaving group, how fast the leaving group leaves, will decide how fast your reaction is going to occur. So a carbocation forms, just like in SN1. Once a carbocation forms, what is its nature? What does the carbocation wants to do? It will want to rearrange. Is there a possibility for this carbocation to rearrange? This is a secondary carbocation. If it goes to this beta carbon, it is still going to be a carbocation. But if it goes to this carbon, it can become a tertiary carbocation. So we see a 1,2 hydride shift. The hydrogen shifts. And we see formation of a tertiary carbocation. So this rearrangement is very critical for your carbocation. The next step is what the E1 mechanism will be for the rest of the part. Now, when you have water, I'm going to use the lone pairs of the water, but you can use any B as your hint. So I have water and I have the lone pairs. In presence of heat, water can abstract out your base here. So remember, this is your alpha carbon on which the functionality is present, and this is your beta. It does not matter if it is an anti-hydrogen or a syn hydrogen. It does not matter at all as long as there is a hydrogen. So the base abstracts out the hydrogen and the hydrogen carbon bond breaks and the double bond will form. So as you can guess, between E2 and E1, so this is your E1 mechanism, between your E2 and E1, who is the faster mechanism? E2. So 95% of your eliminations, 90% of your eliminations will be because of your E2 and not E1. E1 takes its time, just like SN1 does. And always, if any beta hydrogen is present, remember, anti or syn, it will give you the ZSAS product because it takes its time to rearrange. So our E1 always competes with SN1. So this is reaction A, this is reaction B. And we have looked at all our mechanisms, the acid-base mechanisms. We have looked at substitutions, the SN2 and the SN1 mechanism. We have also looked at now the E2 and the E1 kind of a mechanism. I want all of you to explain what kind of a mechanism will we see in these two. And you don't have to answer it right away. Let's do a poll for that. Please go ahead and copy both of these reactions. So I'm only going to focus on A. Okay, that's the one that all of you should have copied. Has everybody copied this question? So your poll has started now. For the following reaction, this reaction A, which mechanism will operate? Think about it. Think about the starting material. Think about the electron donor. And think about what all do you need for all the five kinds of mechanisms. Acid base will definitely compete from both eliminations and substitutions. If it can occur, it will definitely go ahead and occur. Followed by eliminations, because eliminations just need strong base. And strong base with a tertiary substrate, a strong electron donor with tertiary substrate will always give you E2, always. And E1 needs weak base with heat. On the other hand, substitutions, bulky substrates, tertiary substrates cannot do SN2 at all. And SN2 also needs a strong electron donor. Whereas your SN1 can work with a tertiary substrate and it can also work with a weak base. And so I'm going to give you 5 more seconds after this. 5, 4, 3, 2, 1, 0. That's it. And I see that most of you have chosen the right answer, which is SN1. This is going to be your SN1 mechanism. SN1, because you have a tertiary substrate and a weak base. So the leaving group leaves, the incoming attacks, deprotonation will also occur. And then I will get this product. But as soon as the temperature has increased, what is the room temperature? Anything between 20 and 25. If you are given a temperature above it, you're heating it. And so with a weak base and a tertiary substrate, you are going to get the E1 mechanism. The leaving group leaves, the beta hydrogen will be abstracted out. Why this hydrogen and not why these? Because you will be needing to make a ZSAS product, not a Hoffman product. This is a Hoffman product. This is going to be your major product. Any questions? Okay. What if you have a structure like this and H2SO4? Now, before we go ahead and do this, I want you to tell me what kind of alcohol is this? Is this primary, secondary, or tertiary?
Secondary.
Very good. all of your secondary and your tertiary alcohols undergo E1 elimination to dehydrate. What does dehydrate mean? To remove water. The dehydration always occurs for secondary and tertiary alcohols by E1 mechanism. For your primary alcohols, we use similar
Excuse me,
material.
what?
Go ahead, go ahead.
What you mentioned in above the arrow? Connect. What is it?
Where are you asking, Sammy?
Above the arrow.
Above the arrow, concentrated
Mm.
H2SO.
Okay, thank you.
Yes, concentrated H2SO4. So when I say concentrated H2SO4, H2SO4 has a very high molarity. Okay, for example, HCl is 12 molar in its maximum capacity of concentration. Similarly, H2SO4, it can range anywhere between 15 to 30 molar. So anything that is concentrated. Oops. For your primary alcohols, the E2 elimination is followed. Okay. So when you will be doing E1, because of the carbocation formation, the carbocation is going to jump from a secondary location to a tertiary location. And at that point, this carbon and this carbon, both of them will become the beta carbons. So both this carbon and this carbon will give you the major products of the Z-cells. So remember, whenever you will have E1 or SN1, you should expect rearranged products. What about this? What kind of a reaction will occur here? Acid base or a SN1, SN2, E1, E2, or no reaction? What do you think is going to happen here? So paying attention, we have a secondary substrate. And what kind of a donor do I have here? I definitely have a weak electron donor. This is a very weak electron donor. Do you think a E1 or SN1 can also occur? No reaction. No reaction will occur with these. Now, elimination is also going to be an important part for your synthesis. And let's try doing these examples. So let's do the reaction of this substrate with NaNH2. Okay, before you start to look at an example, before you start to look at the reaction, you should always check for acid base, the electron donation, the substrate, the leaving group, and the solvent. Remember all of these conditions. What will happen when you react this reagent with sodium ethoxide? What would happen if you react this with potassium terbiuroxide? What would happen if you reacted with ethanol? And what would happen if you reacted with CH3OH and heat? And so with all of these, I want you to give me the mechanism also. The mechanism that will be operating. Same substrate. It's a tertiary substrate. Remember this carbon is a tertiary substrate. So I'm going to give you all a few minutes to go ahead and copy this and start writing the answers. Think about it. Again, think about the substrate. We all have the tertiary substrates. Think about the electron donor. Is it going to be a base only, or acid-base reaction, or an elimination reaction, or a substitution reaction? Think about it. Now, I just want to remind you that practicing these questions is definitely going to help you a lot. Anyone wants to start with the first one?
SN2.
Okay. And what makes you think that? This is a tertiary substrate. A tertiary substrate will
Sorry, it's SN1. No, the acid base.
So where is the acidic hydrogen here? I know that this is your base, but where is the acidic hydrogen here?
No, nothing.
There's no acid base. Definitely not acid base. Not SN1 also, because I have a very strong electron donor. What is the probability I am going to have E2? Strong base, tertiary substrate will give me an E2 mechanism. The only thing that I have to find is which beta hydrogen should I use? If I go here or I go here, it's going to be the same product. So good try, Sammy. This is going to be my major product. Who does not understand this? Okay. What about with this reagent? Strong base, tertiary substrate. What kind of a?
I don't know.
Strong base, tertiary substrate. Strong base, tertiary substrate. What mechanism was going on? E2.
E2.
Strong base, tertiary substrate. What mechanism would go on? Still E2. Okay, similar product. Again, strong base, tertiary substrate. What mechanism will go on?
E2.
E2. But what kind of a product will I get? Because these were regular sized bases, I now have a bulky base. I was having ZSAF's product, but now what kind of a product will I get? A Hoffman, the less substituted alkene. Are you all with me so far?
Hoffman.
I'm sorry?
That means it's Hoffman.
This is the Hoffman, yes. Yes, the Hoffman. ZSAF's Hoffman. What about with D? Anyone else wants to join? I'm guessing. You have a tertiary substrate and you have ethanol. Is ethanol a strong electron donor or a weak electron donor?
Weak.
Very good. It is a weak electron donor. Why? Because I only have this lone pair here. Is there anyone who does not understand what's going on? Taylor, are you here?
Yes.
Taylor, do you understand why is this a weak donor?
Because of the ET.
Because of the lone pairs of the oxygen. Okay, if you had a negative charge, just like you had negative charges here, and the sodium ion, you have a negative charge on the oxygen, that would make it a strong donor. But here, I don't have any formal charges, I only have a lone pair. Okay, so this is a weak base. Armani, are you here? Armani base?
Yes.
Okay, very good. What kind of a substrate do I have here? A tertiary one. And I have a weak electron donor. What did we talk about? What kind of a mechanism will this reaction have? Take a guess, take a guess. Don't worry, you may be wrong. Nobody else is brave enough to take a guess also. So tell me, take a guess.
Wait, what did you ask me again?
What will be the mechanism of reaction between this substrate and this reagent?
SN2.
Okay, that's a very close enough guess, but SN2 will never work with tertiary, and SN2 needs a strong base. Okay, so it is a substitution, you're right. But Armani, which is the other substitution that we have looked at? Go ahead, tell me. Besides SN2, which is the other substitution? Because this reaction cannot fulfill all the conditions that SN2 needs, what reaction will I see here? What mechanism will I see here? Okay, so we are going to see
SN1.
SN1. When I see SN1, the bromine will leave first, a carbocation will form, and then my ethanol is going to attack here. ETH, and then the deprotonation of this will occur, and then my substituted product will form. OET. So this is OET. So that's my substitution product. On the other hand, when I have a tertiary substrate, a weak electron donor with heat, now what kind of a mechanism will I have?
E1.
Elimination and E1, yes, very good. So you have to look at the substrate, the electron donor, and other reaction conditions also. So definitely the major product will be the ZSAMS product. What about the chemical reaction here? I have a secondary substrate. I have a strong base. And if you remember a few days, yesterday, we looked at this setup.
This is to SN2.
E2 will
SN.
be your major product. And SN2 will be your minor product. And this is what I wanted to explain. Whenever there will be a competition between E2 and SN2 in secondary substrates, E2 will always be the winner. If you had a primary substrate and a strong base. Now your E2 would be the minor product and your SN2 will be the major product. So this is something that you have to remember. If you have a strong base, you are going to get an E2. If you had a weak base, so for example, I'm going to use the same substrate here. And I think we did this yesterday also when we were looking at different nucleophiles. If I have a material which is only nucleophilic and not basic, now my base is not strong. This is a resonance stabilized structure. And so it is not going to be a base. It is a nucleophile, but not basic enough. It is a weak base. Now my SN2 will be the major product. Remember, all the mechanisms are competing. All the other mechanisms will also be happening. But which mechanism will prevail? You will have to decide it based on the substrate, on your electron donor. Do you all understand why this is the weak base? Just because it is resonance stabilized. So if I have a system like this, a secondary substrate with a weak reagent, there was no heat. So I know I'm going to have SN1. OTF is a great leaving group. And so the leaving group leaves on its own. This is a secondary carbocation. The secondary carbocation would want to jump here or there. It can come here or it can go there as well. So just for fun's sake, I will have multiple kinds of products happening. Let's go this pathway where the methyl is shifted here. I still get a tertiary substrate. Or if this hydrogen goes and I get a tertiary substrate, at this location. Both of these products have a tertiary carbocation, and both of these can form my product. So if I have a incoming, this is my incoming nucleophile, my OH can be here, my OH can be here as well. So from this reaction, because of rearrangements, I can get both these products. Equal amounts probably. Maybe one of them will be more, the other will be less, but almost similar amounts. So you should also be able to figure out the types of products that are possible from a reaction. If I had the same reagent, and now I'm using a strong base, what is the product that I'm going to get now? I will get the zitsabs. Oops, did I do something wrong? 1, 2, 3. The zip-sabs product. E2. And another strong base that we used today is right here. Cl. Sodium amide. So I have a sodium amide. I have a secondary, oh, actually this is a tertiary substrate. This carbon is attached to 1, 2, oh, secondary substrate. 1, 2 carbons. This substrate is secondary, NaNH2. This is a strong base, so I definitely would want to go with the E2. There are no hydrogens on this carbon, only hydrogens on this carbon. The base abstracts the hydrogen, bond breaks, leaving group leaves, and you're going to flatten out this molecule. So this hydrogen and this methyl are going to be on the same side. Whereas this group and this group, this terbutyl, are going to be on the same side. So you have to be careful where you're abstracting out your hydrogen from. So do you need a rotation here? You don't. You needed the rotation in the earlier part, but not in this part. So recognizing your E1 and E2 eliminations are very, very important. And let's look at some more examples if everybody feels a little better maybe. If you look at this, is this a strong nucleophile or is it a strong base? It is a weak base. Why? Because nitrogen appears something like this. This is the azide kind of a reaction. But it is a sp2 hybridized carbon also. And so all of these orbitals can accommodate the negative charge better on them. So it is a weak base, but because of the negative charge on it, it is a strong nucleophile. And so it is not a base. I have a secondary substrate. I will get a SN2. If SN2 will always give me the inversion in stereochemistry. Okay. Let me give you some more examples, and why don't you try this on your own? I have this iodide, this, and OMS. with this. You can also do sodium cyanide. So you have these 1, 2, 3, 4, 5 reactions. Go ahead and figure out what mechanisms will employ here. And I'm going to give you about 6-7 minutes to write it out and solve these. Of course, you can use your notes and all the other data, all the other lecture slides and everything like that. Okay. Go ahead and start doing these. So think about these things before you make your attempt at doing these. Do you want the answers to these questions? If not, then we can proceed to the next part of this chapter.
We need to answer, please.
If we need to answer, then all of us will have to work on them together. And I might have to see other students' work also. If not, you can come to the office hours to get the answers to these.
Oh, can you just post them on Brightspace as well?
No, I want all of us to discuss these. And I'm assuming that no one except the two of you are interested. So maybe I'll email the answers.
Oh, yeah, I would like to see the answers as well.
No, there's no seeing the answers. We will do the answers together. So you will be solving the answers. I will be just looking at it. You can solve for these and then email me or send me your office during my office hours. You can come and then I'll give you the answers. So actually, these are very good questions. You can see them on your exam and drill tests, of course. But if you want, all of us can solve this right now, right here also. If everybody will want to solve for it and help me figure out where are we. Do you want to do that right now? Does everybody want to do it right now?
For me, yes.
Okay, 1 versus
Yeah.
3
Yeah.
versus 4, 4 versus 10. Let's just proceed to the synthesis of alkenes then. If you do these questions, you can send those to me and I'll check those for the 4 of you and whoever is interested, of course. So the synthesis of alkenes. What we have looked so far for the E2 and the E1 elimination, we have figured out that from alkyl halides and from other leaving groups, when we do their removal, we will get the alkene. The other method is by dehydration. From the secondary and tertiary alcohols, doing the E1, we can get the alkene, and from primary alcohols, we do the E2 elimination. So for example, if I have a structure like this, I have H2SO4 and heat. What kind of an alcohol is this? It is a secondary alcohol. What kind of an elimination will I get? I will definitely get my
E1.
E1. Where will the double bond form? A ZSAFs product will form. Let's look at this structure, and I have H3PO4 with heat. What kind of an alcohol do I have now? I have a primary alcohol. What kind of a mechanism will work? The E2 elimination will work. Let's look at this one. What kind of alcohol is this? A secondary alcohol. If I'm using my concentrated HCl and heat, what mechanism will run here now?
E1.
E1. If I have another secondary alcohol, oops, and I have any concentrated H, this H comes from HCl, H2SO4, or H3PO4, or for any other, matter of fact, any other proton, along with heat. What is the mechanism that I will see?
E2.
I will
E1.
see E1, yes. And so these are the two methods by which we can get alkenes. So far we had looked at alkenes by the removal of alkyl halides and halide, the other groups that we are removing. Okay, these are the two methods. E2 elimination will always occur when you have a leaving group. A leaving group can be OMS, OTS, OTF, chloride, bromide, iodide. But in case of dehydration, when you're looking at E2, what is the leaving group? The water molecule is going to be your leaving group. So let me quickly do a mechanism which will help you see better. Let's see, here's the example. Let's look at a secondary alcohol first. And I think I drew this example a few minutes ago, so I think I'll just go with it. Concentrated H2SO4 in presence of heat. Now remember, OH is a bad leaving group. What does this concentrated acid do for us? This acid is going to do the acid-base protonation. The first step is the protonation of your group. Once the protonation has happened, remember OH is a bad leaving group. For a secondary alcohol, E1 will proceed, in which the leaving group leaves first. So your leaving group leaves and a carbocation will be formed. Carbocations, what do carbocations do? Carbocations are going to rearrange. So this hydride shift will occur and this tertiary carbocation will form. This is your alpha carbon. These are your beta carbons. Within all of these three you can choose any hydrogen. Why? Because all of them are going to give you a ZSAF's product. So if I choose this hydrogen, the base to come abstract out this hydrogen, break this bond, I will get this particular product. If my base comes and abstracts out this hydrogen, don't you think we are going to have a same product? If my base comes and chooses this hydrogen, then this product will form. And all of them are tri-substituted. Across this carbon, both the hydrogens, across this carbon, one of the hydrogens has been substituted. So tri-substituted, tri-substituted, tri-substituted alkene. Both of these are exactly same compounds. So both of these products are possible. Both of these alkenes are possible from this. If you have to choose only one kind, not within the ring, outside only, you have to convert OH into a good leaving group before you can actually think where will this leaving group go to. Okay. So with a primary alcohol, when you have the concentrated, you still need to show heat. This will be your E2. Primary alcohols undergo E2. The first step will be formation of a good leaving group. Now, because it is a primary carbon, it will take no time for the E2 to occur. So this is your alpha carbon. This is your beta carbon. You need the hydrogen of beta carbon. A base will come, abstract out this hydrogen. This bond breaks, leaving group leaves. So all of these happen in a concerted motion. And you get your dehydrated alkene. So just to remind you, when we form alkynes, we just do a double E2. So 2 E2 eliminations will be required, and we always use a very strong base, a base stronger than sodium hydroxide, which is sodium amide. Now you can either start from vicinal leaving groups. What does vicinal mean? Vicinal means on adjacent carbons. So for example, I can have OMS here, and I may have another leaving group, Br here. So my vicinal leaving groups, and of course other groups. Or I can have a geminal leaving groups. Geminal just indicates on the same carbon. So my OMS and my bromine, both of them are on the same carbon. Not on adjacent carbon, but on the same carbon. That's what the geminal means. A third way from which you can make alkynes is when you already have a double bond. And we will look at this reaction again very closely and more completely in our next module. Br, Br. Just like we have hydrogens attaching across the carbons, we can have our halogens adding across the same way to both the carbons. So remember, we discussed at the beginning of this that our alkenes are more reactive than our more reactive than our alkanes. Why is that? Because the hydrogen can add across these carbons in presence of a catalyst. Alkanes are more stable, alkenes are less stable. So in the same way, we can add our halogens across the carbons. Once you add these, what have you generated? You have generated your vicinal leaving group. Okay. So when you're looking at the alkene formation, you have to look at double E2 methods. So synthesis requires you to check number of carbons in your starting and your ending material, any functional group transformation, FGT. Are you making a double bond? Are you substituting? Are you doing an acid base? That would help you decide what kind of a mechanism and reagents do you need. And in your product, do you have any rearrangements? What has happened to the stereochemistry? What has happened to the regiochemistry? So let's look at an example. For example, you have to form this from this material. So you have to start from here and end here. What is the number of carbons? The number of carbons is exactly same, 1, 2, 3, 4, 1, 2, 3, 4. So you don't have to make any changes to the number of carbons. But what has happened? What is the functional group transformation? From an iodide, you now have a double bond. So what is it that you would think about? You know that you will have an elimination. What kind of an elimination? This is a primary substrate. You should use a reagent in such a manner that you get a Hoffman product. This is not a substituted alkene. This is a less substituted alkene. So you do want to plan an E2, but E2 with an anti-beta hydrogen and a strong base. So looking at it, what is it that you should use to get this product? This is your alpha carbon, this is your beta carbon, and your alpha beta is where your new double bond is. What will you use here? You will use a strong base. You can use a sodium ethoxide, or you can use a sodium amide, any strong base that you would want. This is just one step reaction from a starting material to your final product. Also, if you had used a material like this from BR. So looking at these two, you need to start from here and you need to end here. What is the number of carbons? Exactly same. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Is the connectivity difference? There's no connectivity difference. The functional group transformation from bromine, you have now a OH. So what kind of a reaction has happened? A substitution reaction has happened. Because there is no rearrangement and SN2 is usually the more faster substitution, you should pay attention to a SN2. Yeah? You can also go with SN1, but SN1 will give you rearranged products. This is not a rearranged product. So I will stick to SN2. So what do I need to make here? I need a OH. What is the balancing factor? Would I put a H here to make it a protic acid, or should I put a metal ion here to make it a stronger nucleophile? Definitely for a SN2, I would stick with NaOH. Now remember, whenever you will have a secondary substrate and you are using sodium hydroxide, there is a possibility that E2 will be the major product. However, for synthesis like this, you can use these reagents. Okay? And if you want to undergo a SN1, which this reagent can, or H2O, which will be via your SN1 mechanism. Okay. So you want to make this into this. So read your question carefully. What is being asked? Do you want to have from this to this or this from this? Please read the question. Most of these calculations that we do are something that most of these problems that we do, students are usually not starting from this right place. So in this particular case, number of carbons is exactly same. Functional group transformation is a substitution. Why? The OH is now a Cl. So you definitely have a substitution. However, if you look at your substrate, your electron donor, your leaving group, is your OH a good leaving group? No. So you have to introduce a good leaving group. And if you use the protic part, you may rearrange your material. So I'm going to stick to MsCl pyridine. OMS. Now I have a good leaving group. I can just use my SN2 reaction where the chloride will kick out this OMS. Okay. I can also use HCl here. Using HCl will make my OH into a good leaving group. But I also have this problem of carbocation formation. The carbocation will rearrange. Of course, in this case, it cannot rearrange. But if it can, you should avoid using the protic part. So the Cl will attack and I will get my chloride. So 1 or 2 step synthesis is something that all of you must know how to do and what to do. The most important of these is when you have to increase the number of carbons. So let's say that I ask you to make this from this. So your number of carbons has definitely increased. So 1, 2, 3, 4, 5. Do you see those 5 carbons in your final product? 1, 2, 3, 4, 5. What is extra is these 2 right here. So number of carbons has definitely changed. You will start from this alkyne, 3, 2, and 1. But I wanted to remind you this hydrogen and this carbon, they are not reactive yet to become a nucleophile, to be added onto something else. You will have to introduce an acid-base reaction. So an acid-base reaction is first going to abstract out this proton, making it a C negative. And a sodium ion. Now what do I have here? I have a nucleophile. Remember, this is a weak base also. It's a stabilized kind of a electron donor, conjugate base. It's a stabilized conjugate base. It is just a nucleophile. It is not a base. I will use a primary alkyl halide here. Whenever you have to increase your number of carbons using a alkyne, you need to use a primary alkyl halide so that a SN2 mechanism can go on. So how many carbons are here? 2 carbons, CH2, CH3, and that's what I'm going to place here. CH2, CH3 with a leaving group. Now I cannot just write Lg here. I will have to give a legitimate or reasonable leaving group. And I can just put OMS here. I can put Cl here or anything that I want as my leaving group. So now when the nucleophile will attack, the nucleophile C negative attacks my electrophilic carbon, leaving group leaves, and I will get this long compound attached to this carbon. You can call that 1, 2, 3, 4, 5. It's exactly this compound. Just remember that you have to make sure that your alkyl halide is primary in nature. So I want all of you to practice more and more of these problems. For the next module, which is module 9, I want all of you to be ready and brace yourselves, because we are going to go and look at several chemical reactions left and right. And there will be a lot of memorizing that all of you will need. So after this module, make sure that this weekend you dedicate yourselves to all the 5 mechanisms that we have looked at, and then start making flashcards from tomorrow onwards, because module 9 is very extensively going to be a lot of chemical reactions. Okay, I don't want to scare you. I just want to prepare you so you can plot your time wisely. Okay. All right, I'll see you in a few minutes in the drill section, and have a good day, all of you.